Great. Thank you so much for inviting me to present at this event. I'm going to talk about this work on anomaly detection with tensor networks based on this archive paper that I did with my colleagues at X, Chase, and Giffray, along with our intern Jensen, who is now entering, I believe, his junior year as an undergraduate at Stanford. And he's just great. He deserves, I think, the lion's share of the credit for this work. So what are the takeaways? Let me just give you some of the upshots here. Tensor networks, which many of you are familiar with, and I'll assume a little bit of familiarity with tensor networks. Tensor networks for us are used for parameterizing and computing efficiently large linear operations in very large dimensional vector spaces. How large? Well, exponentially large in the number of features of the data set. And we're talking about situations where we might have hundreds, 100, 200 features. Okay, so exponential where the exponent is like 200. Any kind of dense matrix representation of a linear operation on such a vector space would be computationally intractable. So you have to use some kind of sparse representation, and tensor networks provide that for us. Okay. The other, when we did this on anomaly detection task, that was the task. I'll describe anomaly detection in a moment. And we found that it performed pretty well. And what we looked at in particular was an out-of-the-box performance. What does that mean? It means we looked at a number of different data sets, images, tabular data sets of different types, and we used essentially the same kind of model. We have a few hyperparameters that we tuned a little bit, and I'll describe that toward the end. But mostly we used the same model without changing the model in a significant way, going from, say, images to tabular data. Okay. And with limited information about the task or about the data, the model still performed pretty well. In fact, I think that's the real message here, is that compared to the other models we looked at, tensor networks have the best average performance across many different kinds of tasks. And so my view, and our view, is that this gives a good baseline for future specialization. If you did take into account certain properties of the task and did some more fine-tuning, you could perhaps get push the performance even more. Okay, so there's a lot of knobs to turn and levers to pull to get that extra performance out. This work is just to get started in that direction and to provide evidence that it might be a good idea to do more. There are many, over the last, 5 years or so, tensor networks for machine learning have become, kind of a hot topic. Here's a small collection of authors, including, several people who are here, who have worked on this topic, and there are many that I've left out. So anomaly detection. Let me talk about anomaly detection. What does this mean? The problem is to classify, given an instance of data, whether it is a normal instance or an anomalous instance. Okay, this is different from an ordinary classification task in a couple of ways. So an ordinary classification task, say with two classes, say cats versus dogs, would say, here's an image. I'm going to tell you beforehand it's either a cat or a dog, or that's one of two classes, and you're just going to tell me which one it is. Okay. And anomaly detection is a little bit different. Anomaly detection, instead of cat versus dog, it's more like cat versus non-cat. Okay, where the non-cat doesn't fit into a nice class of its own. It's just anything that's not a cat. Okay, that's one difference. So it's almost like a one versus many classification, except the many is very unstructured. Okay, it's just anything that's not cat. That's difference number one. So the space of outliers, the space of anomalies, is very large, much larger than the space of inliers, typically. So that's sort of like what you see on the right here. The second difference in anomaly detection is sort of a technical difference that's related to the first one, is that during training, when we do an anomaly detection problem, we only show the model normal instances. And then during testing or validation, we show it both anomalies and normal instances. So it's only trained on normal instances and then expected to be able to tell whether it receives a normal instance, something drawn from the same distribution, so to speak, or an anomalous instance. And this gives you a hint as to why deep learning has limited efficacy on this kind of problem. Deep learning is sort of a big data technique, and by construction, anomaly detection, you don't have big data on the anomalies. You have your normal instances, and then there are a lot of, there's a lot of anomalies out there, and you're never going to be able to see them all. You're never, in terms of collecting a training set. And then, in fact, when we actually do the training, we don't even attempt to do that. We just have normal data during training. So rather than use some kind of nonlinear model, nonlinear deep learning style model, we're just going to use a linear model with a bit of a trick or a twist. It's a linear model on an exponentially large space. Okay, linear models are simple, but when you use an exponentially large space or a very large space, you can get something very non-trivial. And this is familiar from the intuition of quantum mechanics. Quantum mechanics is a linear theory of physics, but it can capture all of the nonlinearities present in classical mechanics. The trick, of course, is that it's a linear theory or a linear model on an extremely high dimensional space. How high? Exponentially large. Okay, I mentioned this before, but now I'll give another example. In the case where we're dealing with images, say black and white images of some number of pixels, the exponentially large space is exponential in the number of pixels, meaning that every distinct black and white image, even with one pixel different, forms a new linearly independent direction in that space. Okay, so this means if you have n black and white pixels, we're talking about a 2 to the n dimensional space. Generalizing from there to something like grayscale, you could do that in a variety of ways. One sort of straightforward way, which is the way that we use, is to interpolate. A grayscale image is like somewhere in between a couple of black and white images or multiple black and white images. So a grayscale image can be viewed as a linear combination of black and white images, where the linear combination is determined by the grayness of the pixel. And there are many ways that one can do that. Okay, so this feature map, which takes you into this high dimensional space, is one of the knobs you get to turn. But the point here is that we're looking at exponentially large spaces, exponential in number of features. Manipulating those kinds of spaces is done using tensor networks, which I've already mentioned. Tensor networks, coming from physics, there are kinds of two reasons that one would use a tensor network. Number one is, as I've already mentioned, it's computationally efficient. It's a good way to deal with the exponentially large vector spaces that one encounters in physics and in the context of today's talk in machine learning. But in physics, we also have learned that different kinds of tensor networks are useful for different kinds of problems. You should use a tensor network whose topology, whose sort of graph, encodes in a nice way the statistical correlations of your problem. That's where it's most effective. So for example, the MPS or MPO type tensor networks, which are the ones we'll be using today, are useful for 1D problems where the correlations are local. So we would say low entanglement in the quantum context. So coming from like a local Hamiltonian. And this is, you would not use a matrix product state type representation on a 3-dimensional problem. I mean, you could try, but it is probably not the best idea, or it may not be the best idea. So we are using matrix product states because of their computational efficiency. We're not going to pay so much attention to what the structure of the problem is in terms of putting these things together. So matrix product states have been used on images before, and images are, well, they're local in 2D at least. which is, close to 1D. But one would expect that for images, maybe a different kind of tensor network might be useful. And on tabular data, who's to say if there's any kind of spatial locality at all? We're mostly using matrix product states because of their computational efficiency, the fact that we know efficient algorithms for computing with them. And a matrix product state, no matter what problem you're given, matrix product states are simple enough that that's the thing that you start with, okay? And the spirit of this work is that we're just getting started. So that's why we use matrix product states. So more on that later, but this is motivation. So let me review the model and give you some of the ingredients. The model contains two pieces. Number one is a feature map. So we start with some data. Black dots are normal. The other shapes are anomalies. And we begin with a feature map phi, which takes that normal data and maps it into the very high dimensional embedding space. Okay. I'll say some more about the feature map in a second. But the second step is to take that very high dimensional vector space and perform a linear map into a target space. The objective after the linear map is to get all the anomalies to be annihilated. Okay, meaning they all get mapped into the origin, while the normal instances remain non-zero. And then we can, decide what's anomalous and what's not anomalous by just looking at whether they are annihilated by this map or not. That's the goal. And as you can see in the picture here, it's this linear map, the second step, which is performed by a tensor network, here depicted as an MPO. So let's say a few more words about this feature map. So this feature map takes our data and maps it into a very large vector space. How does it work? Well, we construct this feature map by kind of concatenating or taking the product, the tensor product or outer product of many local feature maps. Okay, so each feature, we can treat each feature as some number. Our features are all going to be real numbers. We'll take them to be between 0 and 1. So sort of like the grayness of a pixel can be mapped into an interval 0 to 1. And we're going to take that feature and map it into a local feature space, p-dimensional space. P could be 2 or 4 or 6. And then concatenating those together or taking a tensor product of all of those to get a mapping of the entire data point into a p to the n dimensional space if there are n, capital N features. Okay. Now, obviously, there are many choices to make with this feature map, and I'll describe in a little bit with a little bit of detail what we chose as our feature map. But this is one of those things that different choices of feature map could lead to different results, and it's an area of exploration. I won't say too much more about that. The other thing about this feature map is, as indicated previously, ultimately it's the magnitude of the data point in the vector space, which is going to be important in deciding anomalies versus non-anomalies. So we begin at the level of the feature map without treating all data points equally as far as magnitude goes. So our feature map takes us into the hypersphere in the very high dimensional embedding space. Okay. So so all data points are treated equally. The other thing to note about the feature map is that, at least for us, it's fixed. It's not something that we train. It's just something that we choose beforehand and then fix forever. One could consider a generalization where this feature map, this nonlinear feature map, is also something that is part of the training. But we have not done that, and I'm not aware of other works which do that either, but could be interesting. The thing that we do train is the linear mapping. Okay, the linear mapping from this high dimensional embedding space to a lower dimensional, but still exponentially large target space. So lower dimensional, meaning, lower dimensional by a lot. So the target space has a still exponentially large dimension, but the exponent is different, meaning that it's, in terms of just absolute magnitude, the dimension is very small. So most vectors in the embedding space are annihilated by this linear map. And this makes sense because most most pieces of data, most possible pieces of data are anomalous. If you think about images, most black and white images look like static, which are, according to any definition of normal, any real life definition of what a normal image is going to count as anomalous. But we want all of our anomalies to get annihilated by the map, and which includes, even beyond just the space being exponentially small, not exponentially small. It's still exponentially large, but much smaller than the original space. We still want to annihilate most of the vectors. The normal images should still be sort of a small subspace within the larger space. The decision boundary for our ultimate ultimate task is going to be some sphere, some hypersphere in the target space, and you can choose the radius of that sphere as you will, depending on your tolerance for false positives and false negatives, and say everything inside of that sphere counts as an anomaly. Everything outside of that sphere counts as normal. The training is done machine learning style using, gradient descent, and we construct a loss function which balances pressures from two different forces. The first term here is the term which involves the data. So these x's are normal instances. Remember, we don't train with anomalies. We only train on normal data. So we take a batch of normal data, xi, and we compute the magnitude of the vector after taking these xi's, mapping them using phi, and then p here is the linear map, p for projection because it's sort of projecting out the anomalies. P maps us into the target space, and then we look at the magnitude of that and take the log for numerical stability reasons. So we want the magnitudes of the normal instances to remain non-zero. That's the job of the first term. And then the second term, which looks like a regulator, penalizes you for just having a very large operator norm on the linear map. So you're better off whenever you can taking the singular values of the operator map to be small. So you want all of the singular values which are not dealing with the normal data points are pushed to zero, basically. And so this helps us annihilate the anomalies. So these are the two terms in the loss function, and that's how we train. So now I'll say, just in terms of an attempt to be self-contained, I'll say a few words about tensor networks, which I assume most people watching this are familiar with, but just to kind of get us all on the same page. A bit of Tensor Networks 101, just a couple of slides. So tensor networks, so a tensor, these graphical notations for tensors are just arrays or generalizations of scalars, vectors, matrices to higher dimensional arrays or higher order arrays. And the problem here is that, or the difficulty is that the number of coefficients in a tensor, the number of numbers in a tensor, rises exponentially with the number of legs. So if each constituent sort of local vector space has dimension d, then adding a leg multiplies the number of coefficients by this number d. And so the amount of memory, if you wanted to store this tensor in a computer, is exponential in the number of legs. And it's also, manipulating these things, doing tensor multiplications would also be exponential in terms of time. It's a bad idea. So tensor networks come in by, you take one of these large tensors and you say, well, I don't care about the most general case of a large tensor. I only care about certain instances. And so what I do is I say, I'm going to assume that my tensor can be well approximated. The tensor I actually care about can be well approximated by, say, a combination of lower order tensors, as shown here in this matrix. This would be a matrix product state approximation. And in this kind of situation, for example, instead of being exponential, the number of coefficients is only linear in the number of legs. So I switched notations from D to P, so P and B. So P for physical, is going to be the dimensionality associated with each of the dangling legs, each of the lower legs. Those are the physical legs. And B is the dimensionality of the edges connecting the tensors in the MPS. So those horizontal legs are dimension B, B for bond. That is the bond dimension. And those are the bond indices. So each of those small tensors with 3 legs has P times B squared coefficients in it. And B is just some, P and B are just sort of fixed numbers. B might be quite large, but the point is it's independent of N. And so adding an additional tensor only increases the number of coefficients linearly on the MPS as a function of the number of legs. So, so this is where you can get your savings. Okay, and for us, our tensor networks that we're going to use would naively be exponential, like on the left, but are only going to be linear when we represent them in terms of tensor networks, like on the right. So now let's draw some tensor network pictures of how these sort of maps are constructed in our case. So first, we go back and we talk about the feature embedding. So there are 2 steps, remember. There's the feature embedding and there's the projection. So the feature embedding, first, we take our image, our raw data. It doesn't have to be an image, but I'll keep using the image as my example. It could be tabular data. And we say, all right, let's just translate this into a bunch of numbers between 0 and 1 rather than an image. So the x's are all between 0 and 1. So they could be the normalized grayscale values of each pixel, n pixels, say. And then our feature map consists of a product. So that we have of local feature maps. So this, in a tensor network notation, this would be tensors which are not connected to each other. And each of those, for example, if P was equal to 2, the local feature space was 2-dimensional, you could look at the sine and the cosine of the grayscale value in order to construct a local vector with unit norm, and then put those together to get something on the hypersphere in the 2 to the n dimensional, P equals 2 to the n dimensional space, embedding space. This is just one possibility. There are other generalizations if you wanted to make P not equal to 2, so P equals to 4, for example, which we do sometimes for tabular data. Then we would have to get 4 numbers out of each x, and one choice there, choice that we take, is to choose, again, sine and cosine, but with a different frequency. Look at higher Fourier modes of x. The point is there are many options here. I'm not going to go into more detail about what options to pick, but anything that gets you on the hypersphere is a fine idea. The next step is to look at this linear map P. So remember, we have physical dimension P, bond dimension B. This map is a mapping from the lower indices, the P to the n dimensional space, into the red upper indices. So there are fewer, there are only, rather than having n, there are n lower indices, but there are q upper indices, and q is basically n divided by s. So we skip every s nodes when putting an upper index. So the target space has much lower dimension, but still exponentially large in n. And this, the data in these A's, in these tensors, are the training, or are the coefficients that we train. Okay, these are the variational parameters. The linear map is just obtained in tensor network language like this. We take the features and we map it. And then the terms in the loss function are easily constructed. You know, the experts will recognize this. Will recognize these as just the norms of the operator norm and the norm of the mapped features. It's important, as I mentioned before, that we have efficient ways of computing with these tensor networks. Just writing down a tensor network doesn't mean it's automatically efficient. You still have to be a little bit careful. So I'll just, for the experts, flash a few slides about how the computation is done. It's not going to be a surprise to anybody. So the upper diagram here in particular, you contract the legs in a certain order to turn the upper diagram into something that looks like the lower diagram. So the lower diagram looks like a ladder. The upper diagram, after doing a few simple contractions, again becomes a ladder. And then once you have one of these ladder diagrams, it's fairly straightforward to just go down the ladder and do the computation in this way until you get a number at the end for computing the loss function. And based on these pictures, you can write down the computational complexity if you wanted for computing these terms. And it's something that is under control, and as promised, it ends up being linear in n, the number of features. So we do this, we compute this. This is how we compute the loss function. We mainly, we use gradient descent after initializing the tensors randomly. There are some details that you can look in the paper for. Again, the predictions of the model are determined by a parameter lambda, which tells you it's some hypersphere in the target space, which tells you which data points count as anomalies and which ones don't. And then as a function of lambda, you'll have different false positives and false negatives and true positives and true negatives and so on. And the area under the ROC curve, which takes into account all of the different choices of lambda, is a typical metric for determining the efficacy of these models. So now let's look at some examples of how this performs. So images, which I've used so far, are the first instance. So we can look at MNIST and fashion MNIST. MNIST, everybody knows, it's handwritten digits. Fashion MNIST is very similar to MNIST. There are 10 categories, but there are different items of clothing rather than different images. So it's like a more complicated, slightly more difficult version of MNIST. These are 28 by 28 grayscale images, but we downsample to 14 by 14 for computational efficiency reasons. So the number of features here would be 196 for the TN model. The models that we compare to, when we compare performance, we don't downsample. So the TN model gets handicapped a little bit because we downsample the images. So that's just a thing to note. And this was for ease of computation. So you can think of this as just a piece of the feature map. The feature map involves downsampling before applying sine and cosine. And then here are the results. So the final column here, there's the tensor network anomaly detection column, TNAD. And we looked at anomaly detection on MNIST and fashion MNIST, where one of the classes, one of the digits or one of the fashion items was treated as the normal instance, and all of the others were treated as anomalies. And then depending on which one you chose as the normal instance, you'd get different results. So the first row is choosing 0 to be the normal instance and all the others to be anomalies, for example. And you can see, the tensor network model, the top two performers in each row are bolded. The tensor network model did pretty well. It was not the top performer, but it was, it did really well as kind of a baseline. The winner, is the undisputed winner here would be this GOAD model, or GOAD. This model is a much more sophisticated model, but it's meant for images. That model takes into account the fact we're looking at images. Okay, the tensor network model does not, and I'll emphasize that again in a second. There are a bunch of hyperparameters here, like the bond dimension, the S, the number of legs that you skip, the alpha, the regularization parameter. In orange here, I've highlighted the default values, but you get mild dependence, the area under the ROC curve. You get mild dependence by changing these hyperparameters. More interestingly, you can look at tabular data, so data which has no spatial anything about it. And here are 5 tabular data sets. And we looked at the same models on tabular data. We chose different parameters for the tensor network in these cases. These parameters were not, we did not do like a serious grid search to figure out what interesting parameters to choose here. These parameters were chosen based on some heuristics, basically determining how large we wanted the dimensionalities to be and estimates of how big the terms in the loss function were. You could read about that in the paper. But it's essentially the same kind of model, but used on very different kinds of data. And the punchline here is that on the tabular data, all of these other models, which are, for the most part, focused on images, did not perform well at all. Whereas the tensor network model actually did quite well. In every instance was one of the top 2. The best, if not, or it was the best. It was either the best or tied for the best in each instance for the tabular data. Essentially the same model. So as a conclusion, I would say that the tensor networks for anomaly detection, they work really well, essentially out of the box. The hyperparameters, as I alluded to, the estimates of the hyperparameters, it doesn't require very super fine tuning. There are additional hyperparameters that you could try to fine tune. So things like bigger things like the feature map and the tensor network topology, which could be chosen to match up better with particular data sets. And in that way, I would expect, the next step, I think, is to pick a problem or pick, images or pick, certain tabular data of a certain type in some, industry or something, and try to squeeze out extra performance by choosing some of these other knobs, by tuning some of these other knobs, adding, choosing a better topology of tensor network or fine-tuning the feature map. But this was, I think, very encouraging initial work, and thank you for listening.